Welcome to Lecture 11, Quantum Computing, Marshall University. Quantum Programming Frameworks. We'll be discussing. This is your Professor T. Freed Muhammad. So, I'm really excited to explore two cutting-edge tools in this lecture that are transforming how we write quantum programs. Today's session is part of our ongoing journey into quantum computing here at Marshall University, and I think you'll find that this technology is becoming more accessible than ever before. As we move forward in the field of quantum computing, having the right programming tools is essential. We are not just talking about theoretical concepts anymore. These frameworks allow you to actually write code, run it, and see results. Whether you are interested in drug discovery, cryptography, or solving complex optimization problems, the frameworks we discussed today are the great gateway to making those dreams a reality. By the end of this lecture, you should feel confident enough to start experimenting with quantum circuits yourself. Don't worry if you're new to quantum mechanics, if you have never studied that, or programming, if you are looking at this lecture or watching this lecture first time. We'll build everything from ground up. This is an exciting time to be learning about quantum technology, and I'm glad you're here and to be the part of it. So let me start by laying out exactly what we are going to accomplish together in the next hour or so. By the time we finish, you'll have a solid understanding of what quantum programming actually is and why it matters. You'll also be able to distinguish between different quantum frameworks and understand their strengths and weaknesses. More importantly, you're going to get hands-on experience. We'll walk through creating actual quantum circuits using both Qiskit or Qiskit and Cirq, which means you'll understand the fundamentals of how to code for quantum computers. You'll see real examples, and hopefully you'll feel inspired to try this on your own computers later. I always believe that learning by doing is the most effective approach. We are going to explore how you can take what you have learned and apply it to the real quantum hardware, which is absolutely not available for us to work with at this moment. One of the amazing aspects of modern quantum computing is that you don't need to own a quantum computer to use one. We'll discuss how both Qiskit and Cirq connect to actual quantum computers in the cloud, so you can literally run your code on real machines. By the end, you'll have all the knowledge you need to get started on your own quantum computing journey. So the interesting question is, what is quantum programming? At its heart, quantum programming is the process of writing code that tells quantum computers what to do. Now you might be wondering, what makes it different from regular programming? The answer lies in how quantum computers process information. While the computers we use every day, this is a significantly important question, so I'm going to reiterate everything once again for the clarity's sake. So at its heart, quantum programming is a process of writing code that tells quantum computers what to do. Now you might be wondering, what makes it different from regular programming? The answer lies is how quantum computers process information. While the computers we use every day, like your laptops and phones, work with bits that are either 0 or 1. Quantum computers use something called qubits, as we have been discussing in quite length. So here's where things get really interesting. A qubit can be 0, it can be 1, as we discussed earlier, but it can be both at the same time. And we all now know, after the 10 lectures before, the phenomenon is called superposition. This is mind bending at first, but it is also the key why quantum computers are so powerful. When you write quantum code, you're essentially orchestrating these qubits to exist in multiple states simultaneously, permitting the computers to explore many possible solutions to the problem all at once. What makes quantum programming so valuable is that it lets us harness the genuine power of quantum mechanics. Instead of fighting against the strange nature of quantum systems, we embrace it and use it to our advantage. This ability to work with superposition and other quantum properties means that certain problems that would take classical computers thousands of years could potentially be solved in minutes on a quantum computer. That is the promise of quantum programming. So now this is another intriguing question. Why quantum programming? You might be asking yourself, why should I care about quantum programming? The answer is that quantum computers are going to revolutionize multiple industries in the coming years. Let me give you some concrete examples. In a pharmaceutical world, quantum computers could dramatically speed up drug discovery by simulating complex molecular interactions that are impossible for classical computers to model efficiently. This could lead to new medicines and treatments arriving faster than ever before. Then there is cryptography and security. Today's encryption methods depend on the and fast acting facts that classical computers find it extremely difficult to factor large numbers. Both a quantum computer could potentially break these encryption systems in days or even hours. This is both exciting and scary, which is why governments and companies are racing to develop quantum resistant encryption right now. If you understand quantum programming, you will be at the forefront of this crucial area in specific. Beyond those headline grabbing applications, quantum computers excel at solving optimization problems. Imagine you're a logistics company trying to figure out the most efficient routes for thousands of delivery trucks. These problems have so many variables that classical computers struggle. Quantum computers, however, could find a better solution much faster. Financial institutions are also interested in using quantum computers for portfolio optimization and risks analysis. The bottom line is that quantum programming skills are going to be incredibly in high demand. What is a quantum framework? A quantum framework is basically a software toolkit designed to help you write, test, and run quantum programs. Think of it like if quantum computing is a language, then a quantum framework is like having a dictionary, grammar guide, and writing tools all in one package. These frameworks do the heavy lifting for you, and you don't have to program quantum computers from scratch. So, what exactly do these frameworks provide? First, they give you access to pre built quantum gates, which are the fundamental operations you use to manipulate qubits, just like a building is made of bricks. Quantum circuits are made up of these gates. Without a framework, you would have to figure out how to construct and control these gates yourself, which would be incredibly complicated. With a framework, you just call a function and the gate is applied. The second major thing framework provide is simulators. Before you send your quantum code to run on an actual quantum computer, you want to test it first. Simulators let you run your circuit on a classical computer, which shows you what your code would do if it ran on a real quantum machine. It's like practice simulator for pilots. Finally, the frameworks like Qiskit and or Qiskit and Cirq give you direct access to real quantum computers through cloud services. This is revolutionary because it means you can access quantum hardware right from their laptop without owning an incredibly expensive machine. So, why should we care for using Qiskit? There are several compelling reasons why Qiskit has become one of the most popular quantum programming frameworks. First and foremost, it is user friendly. The developers at IBM designed it specifically with accessibility in mind. If you have ever programmed in Python, which most of you probably have, Qiskit will feel natural to you. The syntax is clean and logical, and many operations have intuitive names. The second major advantage is the community surrounding Qiskit. There is a massive community of quantum programmers, researchers, and enthusiasts who are Qiskit every day. So, this means that if you get stuck or have a question, there are countless tutorials, forums, and documentation available to help you. You are never truly alone when learning Qiskit because so many people are using it and sharing their knowledge. This community support is invaluable when you are learning something new and challenging. Qiskit's integration with IBM's quantum infrastructure is a huge advantage. IBM operates several quantum computers that are available to the public through their cloud platform, which Qiskit you can seamlessly transition from testing your code on a simulator to running it on real quantum hardware. Some of IBM's computers are free to use, which means you can experiment without spending any money. This accessibility is game changer for students and researchers who want to work with actual quantum computers. So Qiskit was developed by IBM, as mentioned earlier, one of the largest technology companies in the world, as we all know, and it is completely open source, meaning anyone can use it, study it, and contribute to it. IBM has been investing heavily in quantum computing for years, and Qiskit represents their commitment to making quantum programming accessible to everyone. What makes Qiskit particularly appealing is that it provides a comprehensive environment for every stage of quantum programming. You can write quantum circuits using an intuitive syntax, you can simulate your circuits to see how they behave, and you can run these circuits on real quantum computers, many of which are hosted on IBM Quantum Cloud Platform. This end to end approach means you're not jumping between different tools and platforms. Everything is integrated. IBM Quantum Initiative means they are constantly improving Qiskit and adding new features. They have a strong commitment to the quantum computing community, which is evident from the extensive documentation, tutorials, and support available. If you're looking for a framework that is well established, actively maintained, and backed by the major corporation, Qiskit is an excellent choice. So getting started with Qiskit is straightforward, which is one of the reasons it is so accessible. The installation process is simple and works the same way on Windows, Mac, and Linux. To install Qiskit, you use pip, which is Python package manager. You simply type pip install Qiskit into your terminal or command prompt. Once Qiskit is installed, you need to import it into your Python program so you can use its features. The most common imports are shown on the slide, and you will see these same imports in almost every Qiskit program. The quantum circuit class is what you use to create your quantum circuits. The AER module provides simulators and execute functions, runs executing a function runs your circuits. These building blocks are fundamental to everything we'll do with Qiskit today. The beauty of this simplicity is that you can be up and running in literally minutes. There is no complicated setup, process, or special software you need to buy. This low barrier to entry means that students, researchers, and hobbyists can all start experimenting with quantum computing right away. It is one of the reasons Qiskit has become so popular in universities and educational settings around the world. Now let's dive into our first real quantum program. Don't be intimidated by the code on the screen. We are going to break it down line by line, and you'll see how straightforward it actually is. We are creating a quantum circuit with a single qubit, which is simplest possible circuit. Think of it as hello world of quantum programming. The first line creates the quantum circuit, which is technically with one qubit. That's it. One qubit is already to be manipulated, or I can say its qubit is ready to be manipulated. The next line applies that's called Hadamard gate to the qubit. In quantum mechanics, the Hadamard gate is like magic transformation that puts a qubit into superposition before we apply the Hadamard gate. Our qubit is in the zero state after we apply it. The qubit is simultaneously 0 and 1. It is in superposition. This is the beginning of quantum weirdness, and it is beautiful. The final line measures the qubit and prints out the circuit. Measurement is how we extract information from a quantum circuit. When you measure a qubit in superposition, it will collapse to either 0 or 1 randomly. If we already run, or if we were to run, this circuit once, we would get either 0 or 1 with equal probability. When we run it many times, we get approximately 50% zeros and 50% ones. This simple circuit demonstrates a fundamental principle of quantum superposition, and it is the foundation for everything more complex. Now that we have created a quantum circuit, the next step is actually running it. This is where the simulator comes in. The simulator is like a virtual quantum computer that runs on your regular computer. It can't harness real quantum effects indefinitely, but it can be accurately simulating what quantum circuit would do, as long as the circuit is not too large or too complex. The process is straightforward. First, we get simulator backend using AER. Think of backend as the actual machine or simulator we are using to run the circuit. Then we execute the circuit on the backend, simplifying how many times we want to run it. In this example, we are running it 1,000 times. Each run is called a shot, so we are doing 1,000 shots. This repetition is important because quantum behavior is probabilistic. A single run might give you 0 or 1, but running many times give you statistical data about the probabilities. We get the result and print out the counts. This shows us how many times the circuit gave us 0 and how many times it gave us 1. In this particular circuit, you should see roughly 500 zeros and 500 ones because the Hadamard gate puts the qubit into an equal superposition. This hands-on experience with running quantum code is exciting because it connects the theory we have been discussing to actual computational results. Now let's shift our focus to the second major quantum framework we are discussing today. It's CIRQ, C-I-R-Q. CIRQ was developed by Google, the tech giant known for search, artificial intelligence, and now quantum computing. Like Qiskit, CIRQ is open source, meaning it is freely available to everyone. Google has invested billions of dollars in quantum computing research. The CIRQ is their contribution to making quantum programming accessible. CIRQ has a somewhat different philosophy than Qiskit. While Qiskit is general purpose and works with many different quantum computers, Circ was specifically designed with Google's quantum processors in mind. Google's quantum computers have unique architectures and characteristics, and Circ was built to work optimally with that hardware in mind. Circ places a strong emphasis on what's called noise aware quantum programming, which means it is designed to help you write code that works well on today's quantum computers, which are noisy and imperfect. What is interesting is that Circ represents a different approach to quantum programming, where Qiskit might prioritize ease of use for beginners. Circ offers more flexibility and control for advanced users. If you're planning to work with Google Quantum hardware, or if you want more fine grained control over your quantum circuits, Circ might be the better choice. However, the fundamental concepts are the same across all quantum frameworks. So, why should we care, or why we use Circ? So, this is a great question. Another question could be, why should you choose Circ over Qiskit? The first advantage is flexibility. Circ is designed to work particularly well with near-term quantum devices. These are the imperfect, noisy quantum computers we have today. Near-term quantum computers are not powerful enough to do everything we dream about, but they can do useful things if you program them carefully. Circ gives you tools to optimize your circuits for these real-world constraints. The second advantage is customization. Circ allows you to customize and fine-tune your quantum circuits in ways that Qiskit might not. If you are a researcher who wants detailed control over the exactly how your circuit behaves, Circ provides that flexibility. You can control things like the duration of quantum gates, the timing of operations, and other low-level details that might matter for research purposes. This level of control is powerful, though it does mean Circ has a steeper learning curve than Qiskit. The third major advantage is that Circ is designed from the ground up to work with Google's quantum hardware. If your goal is to eventually run your quantum circuits on Google's quantum processors, using Circ means you're building your code in a framework that optimized for that hardware. Google's Sycamore processor and other Google's quantum chips have specific capabilities and quirks, and Circ is built to work with them. For those committed to the Google quantum ecosystem, Circ is a natural choice. Installing Circ is just as easy as installing Qiskit. You use the same Python package manager pip and simply type pip install Circ to download and install the framework. Circ is available for all major operating systems, so installation works the same way whether you are on Windows or Mac or Linux. Once installed, you import Circ into your Python programs just like any other library. The import is simple. You just write import Circ and you're ready to go. After the import statement, you have access to all Circ functionality. You can create qubits, build circuits, apply gates, run simulations, and everything else you need. The simplicity of the installation and important process is a good sign of how well designed the framework is. Just like Qiskit, Circ is free and open source, so there is no cost barrier to getting started. You can install it on your personal computer right now and start experimenting. This democratization of quantum computing tools is one of the most exciting developments in the field. A student with a laptop has access to same quantum programming frameworks that Google's researchers use, which means the possibilities are truly open-ended. Now you're going to build your first Circ circuit, and you will see that it is very similar in concept to what we did with Qiskit, though the syntax is a bit different. We are starting with the same basic idea, a single qubit that will put into superposition using a Hadamard gate. This consistency across frameworks is helpful because it means once you understand quantum concepts, you can apply them in any framework. In Cirq, we start by defining what is called a line qubit. This is Cirque's way of representing a qubit in a specific position on a line. We create a new circuit which starts empty, then we append operations to the circuit. This is how we build up the sequence of quantum gates. First, we apply the Hadamard gate to our qubit, putting it into superposition just like in Qiskit example. Then we add measurement operations that will measure the qubit and store the result. When we print this circuit, we see a visual representation of our quantum circuit. This is one of the nice features of Cirq. It has good visualization tools and help you understand what your circuit looks like. The visual representation makes it easier to catch errors and understand the flow of your quantum operations. Now that we have built the circuit, we are ready to run it on a simulator, which is our next step. Running a circuit is straightforward. We create a simulator object using Cirq's simulator class. The simulator is like Qiskit's simulator. It is a virtual quantum computer that runs on your regular computer. Then we call the run method on the simulator, passing in our circuit and specifying how many repetitions we want. Just like in Qiskit, we are running the circuit multiple times to build up statistical data. When we run the circuit, Cirq gives us back the measurements. Each measurement tells us whether the qubit was in the 0 state or the 1 state when we measured it. Because we put the qubit into superposition with the Hadamard gate and we are running a circuit 1,000 times, we should see roughly 500 of each result. This is the same probabilistic behavior we saw with Qiskit. The main difference between running Cirq and running Qiskit is just the syntax and how results are returned. The fundamental physics and the behavior of the quantum circuits are identical. This demonstrates that once you understand quantum mechanics and quantum circuits, you can apply that knowledge across different frameworks. The tools might be different, but underlying quantum principles remains the same. Now let's step back and compare these two frameworks side by side. Both are excellent choices, but they have different strengths. Qiskit is developed by IBM and Cirq is developed by Google, as mentioned earlier. These are two of the largest technology companies in the world, as we all know, and both are heavily invested in quantum computing at this moment. Both frameworks are open source and freely available, which is wonderful for students and researchers. When it comes to focus, Qiskit is more general purpose. It is designed to work with many different quantum computers and simulators. Cirq is, on the other hand, is specifically focused on near-term quantum devices and real quantum computers that exist today with their limitations and imperfections. Regarding hardware access, Qiskit connects to the IBM quantum computers while Cirq connects with Google's quantum processors. If you care about which quantum hardware you'll be using, this is an important factor in your choice. The last major difference is the ease of use. Qiskit is generally considered more beginner friendly with a gentler learning curve. Cirq offers more technical depth and flexibility, which appears in terms of appealing to advanced users and researchers, but might be overwhelming for beginners. There is no objectively best framework. It depends on your goals, your learning level, and which quantum hardware ecosystem you want to work with. Many quantum programmers actually learn and use both frameworks throughout their careers. To write meaningful quantum circuits, you need to understand quantum gates. Gates are the fundamental operations that manipulate qubits, and they are like the vocabulary of quantum computing. Let's look at some of the most important gates. The Hadamard gate, it's a revision for you all. If you have seen the previous 10 lectures, you know the gates in quite depth. However, for the sake of simplicity, I'm going to go once again. So the Hadamard gate, which we have already used, puts a qubit into superposition. This is one of the most commonly used gates because superposition is the key to quantum computing's power. The controlled NOT gate or CNOT gate is another fundamental gate that is absolutely crucial. It involves two qubits and creates entanglement between them. Entanglement is quantum phenomenon where two qubits become correlated in a way that has no classical equivalent. When qubits are entangled, measuring one instantly affects the other regardless of their physical operation. The CNOT gate is the primary tool for creating entanglement in quantum circuits. The Pauli X gate is the quantum equivalent of classical NOT gate. It flips a qubit from 0 to 1 or vice versa. It seems simple, but it is a fundamental building block. All of these gates and many others are available in both Qiskit and Cirq. The syntax for applying them differs slightly between frameworks, but the underlying quantum mechanics is identical. These gates might seem abstract now, but they are the tools you will use to build increasingly sophisticated quantum algorithms. The quantum circuit is essentially a sequence of quantum gates applied to qubits in a specific order. Think of it like a recipe. Each gate is an ingredient or a step, and the circuit is the complete recipe. The order matters because quantum operations can have different effects depending on what comes before them. You can just apply gates randomly and expect the same result. So you cannot technically apply. So let me walk you through a famous example, the Bell state circuit, which creates an entangled pair of qubits. We start with two qubits, both in a zero state. First, we apply the Hadamard gate to the first qubit, putting it into superposition. Then we apply a CNOT gate with the first qubit as the control and the second qubit as the target. This CNOT operation entangles the two qubits. The result is a Bell state, which is a specific type of entangled state, whether in terms of where the two qubits are perfectly correlated. The beauty of this circuit is that it demonstrates the key quantum properties we have been discussing, superposition and entanglement. With just two gates, we have created a state that has no classical equivalent. If you measure the first qubit and get 0, you are guaranteed to get 0 when you measure the second qubit. If you get one of the first qubit, you will get on the second. This correlation exists when, though the qubits might be far apart, Bell states are not just theoretical curiosities. They are fundamental to quantum computing and quantum cryptography. One of the most exciting aspects of modern quantum computing is that you can actually run your circuits on real quantum computers. You don't need to own the hardware yourself. Qiskit and Cirq make this possible by connecting to cloud-based quantum computers. IBM provides public access to several quantum computers through their cloud platform. Google does the same with their quantum processors. The process is straightforward. In Qiskit, you authenticate your account with IBM using their cloud credentials. Once authenticated, you can access different quantum backends. You can list the available quantum computers and choose which one you want to use. You then execute your circuit on the back end just like you would with a simulator, with one key difference. Instead of getting immediate results, you get a job that's queued to run on the actual quantum computer. There is usually a wait time, sometimes just minutes, sometimes longer depending on the queue. It is important to understand that real quantum computers are noisy and imperfect compared to the simulators. They make errors, and those errors can affect your results. However, despite these imperfections, running a real hardware provides invaluable experience and insights. You get to see how quantum algorithms actually behave on real quantum devices, and you can start thinking about error mitigation and other advanced techniques. The fact that this is available for free is genuinely remarkable and represents a significant democratization of quantum computing technology, as mentioned earlier. Now that you understand the fundamentals of Qiskit and Cirq, you might be wondering how to apply this knowledge. I want to inspire you with some practical project ideas that you could actually build yourself. The first project is creating a quantum random number generator. This sounds complicated, but it is actually perfect for beginners. You use the superposition of a qubit to generate truly random numbers, which is something classical computers can do perfectly. A quantum random number generator has real world applications in cryptography and security. A second project involves implementing famous quantum algorithms. The Deutsch Hose algorithm is a great next step because it is more complex than what we have done so far, but it is still manageable for learners. It demonstrates quantum speed up by solving a specific problem much faster than any classical computer could. Implementing it yourself will deepen your understanding of how quantum algorithms work. You could even implement Shor's algorithm, which is the algorithm that could break modern encryption, or Grover's algorithm, which performs quantum searches. These are algorithms that make quantum computing valuable. My third suggestion is simulating molecules using something like VQE, which stands for Variational Quantum Eigensolver. We have discussed that in quite depth in earlier lectures. Since this is a profound third suggestion, so I'm going to repeat myself. So, the third suggestion that I would like you to look into is simulating molecules using something called VQE, which stands for Variational Quantum Eigensolver. This is a practical technique used in a real world quantum computing research to understand molecular properties. It is more advanced, but it is incredibly satisfying to use quantum computers to simulate chemistry. The goal with all of these projects is to take what you have learned and apply it to the real problems. That hands on experience is what separates someone who has already read about quantum computing from someone who truly understands it. Let's take a moment to review what we have covered today because I think you have absorbed quite a bit. Qiskit and Cirq are two powerful frameworks that make quantum programming accessible to everyone. They are free, open source, and backed by major tech companies. They allow you to write quantum circuits, test them on simulators, and run them on real quantum hardware. These are remarkable tools that didn't exist just a few years ago, and now they are available to anyone with a computer and an internet connection. Beyond the technical details, I want you to appreciate what this means for your future. Quantum computing is no longer a distant dream. It is happening now. Companies like IBM and Google are building quantum computers. Jobs in quantum computing are appearing on the job market. If you are interested in this field, now is an incredible time to build your skills. The knowledge you have gained today positions you to take the next steps and go deeper into quantum computing research and development. My next steps for you are clear. First, install Qiskit or Cirq on your computer. Run the simple circuits we discussed today. Experiment and change the code to see what happens. Second, explore more complex quantum algorithms and try to implement them. Third, join the quantum computing communities online where you can ask questions, share ideas, and learn from other enthusiasts and professionals. The quantum computing revolution is just beginning, and I truly believe that many of you in this class will play important roles in shaping its future. Thank you so much for your attention today, and I'm excited to see where your quantum computing journey takes you in the next lectures.